Bam! Mr. Taru. In this math lesson, we're going to be looking at equations of lines. Now I'm saying equations because unlike before in our studies of math, where we studied or worked with the equation of a line in Cartesian format, now we're going to be looking at the equation of a line in parametric form, and most importantly, because we're studying vectors, the vector form of an equation of line in 2D space. The video after this is going to be in 3D space, and it's a nice extension of this lesson. We are going to do, obviously, some notes here, a couple pages of notes, giving you some vocab and just explaining how to read your textbook. We're then going to look at 3 examples. We're going to be given an initial and terminal point, and or just 2 points that a line goes through, and find the equation of that line in vector format, parametric form, and Cartesian. You probably already remember can think of the Cartesian form of a line, at least in 2D space. Example 2 is going to be given, you're going to be given the equation of a line in vector format. We're going to find 3 distinct points along that line and then test whether a point lies in that line or not. We're going to then, for example 3, write down vector, parametric, and Cartesian equations for the line through a given point that's parallel to some line that whose equation is in vector format. Timestamps, those descriptions are going to be in Timestamps to those examples are going to be in the description, as well as a link to the playlist which I'm developing that includes all my lessons about vectors. So the vector equation of a line, what is it? Well, a point R is on the line AB. So we're looking at my diagram here of this blue line passing through point A and B. That's what we're interested in. And R is going to lie on that line. So basically, we're describing any point that's on this line AB. A point R is on the line AB when AR, vector AR, is equal to some kind of scalar multiple, here we're just using a Greek letter lambda, times vector AB. Okay, so if vector AR is equal to lambda times vector AB, then this point R is on that line. You know, all we're doing is referring back to the test we just learned, the test that we use to determine if 2 vectors are collinear. As long as you're using the same initial point, if one vector is equal to a scalar multiple of another vector, assuming that scalar multiple is a real value and not equal to 0, then those vectors are collinear. Hence, that vector, that point R, is on the line. Okay, so this is called a vector equation of the line AB, though it's not a form of this vector form of a line that we're really going to be working with much. If the point R has a position vector R, the point A has a position vector A, and AB, vector AB, is equal to vector U, the direction vector, then the vector equation vector AR is equal to lambda times vector AB can be written as vector R is equal to vector A plus lambda times vector U. Okay. Never remember saying the word vector so much when we talked about equations of lines in algebra. So where is the connection? Okay, well your position vector, by the way, is of course just when your initial point of your vector is the origin. So my diagram here, that's why I have vector A starting and vector R starting from the origin. They're position vectors. So this vector A is really nothing more than describing where some point is, where some fixed point is in space relative to the origin. And same with this, this vector R, that's a position vector for R. Y, the y coordinate of any point along a line, any point along a line in vector form, is equal to vector A, and what we remember, y equals mx plus b all the way back from algebra 1 is just some fixed point. But, well, b in slope-intercept form had to be a y-intercept. Now we're a little bit more general, but it is still just some fixed point in space. And then our mx is just, well, m is some sort of scalar multiple, if you will, telling you how far or how many times you're doing this rise over, excuse me, got that backwards. X is acting basically as a scalar multiple to m, your slope, how many times you do that rise over run for your gradient or the slope of your line. Well, that's what we got going on here, our lambda, some real multiple of vector u, and vector u is acting as slope. Vector u is how do you move in space to get from point A to point R vector. So if you think of like this is your initial point and terminal point, and you want to find vector AB, you just subtract the horizontal components and vertical components, and you get, well, vector and component form for vector AB. Well, that's our vector u. That's our effectively like our slope in two-dimensional format. So vector A is equal to, remember, our position vector OA, vector OA, represented at a fixed point, and vector u is a directional vector like slope with the scalar multiple. So even though this looks really funny, looks very foreign if you're just stepping into the world of vectors, it is very closely tied to just that simple y equals mx plus b slope-intercept form of a line that we learned all the way back in Algebra 1 and Geometry and Algebra 2 and so on and so on. So this is all related. That's the beauty of math. Next set of notes coming up right now. So here we go. This page of notes is going to allow us to move through vector, parametric, and Cartesian form of a line. If line AB lies in the plane of xy, basically like you're drawing your line on your paper, and your paper is the plane xy, then you can represent the vector in component form, where our vector r is the position vector for any point along our line. So we have a generic x and y. Vector A, again, is our position vector for that first initial point that we use to define the equation of this line. And vector u is the component form of that vector which is acting as our slope. We're looking at, say, like the previous page, vector B, coordinate B and pointer coordinate A, and we're doing terminal minus initial to set up the component form of that vector. This is sort of like our vector AB, if you will. Only our directional vector doesn't actually have to be necessarily on the line, it just has to be in the same direction. So we have vector r is equal to vector A plus lambda times vector u. That was just on the previous page. Now if we write each of these vectors in their component form, well, it is an equation, and the relationship along our x and our y, and eventually as we go into 3D space, our z variables or components, they all have to be the same. And of course, we have that same scalar multiple being applied to this vector. So it's basically like if you actually distribute this, it's lambda times u sub 1 and lambda times u sub 2. So you get x is equal to x sub 1 plus lambda times u sub 1. Going along the y components, y is equal to y sub 1 plus lambda times y sub 2. And this is a pair of equations now. We went from one equation to two. One equation tracking the horizontal movement, at least horizontal in terms of our two-dimensional system, and an equation tracking our movement along the vertical axis or the y-axis. And that's our pair of parametric equations. And these are handy with some types of applications in math and computer science and so, where we can track that horizontal and vertical movement separately. Well, if we take the idea that these relationships, that this relationship between the initial and any sort of arbitrary point of x and initial y and arbitrary point of y, well, that has to be only true if that, of course, that same scalar multiple of lambda is applied to both or each of the components of this sort of directional vector. So that's going to allow us then to go from this parametric form into a Cartesian form by realizing that lambda has to be the same in each of these equations. So we're going to go ahead and bring x sub 1 over and y sub 1 over with subtraction and get x minus x sub 1 equals lambda times u sub 1, and y minus y sub 1 is equal to lambda times u sub 2. Divide both sides by u sub 1, and here divide both sides by u sub 2, and we have a Cartesian form. Now, your book may very well not be calling this Cartesian form for the equation of a line in two-dimensional space, but it will be in three-dimensional space. I'm just trying to tie that together with you here. We know three forms of the equation of a line in sort of like a Cartesian format. We have standard, point slope, and slope-intercept form. This does not look like slope-intercept form, but we don't have that simple y equals mx plus b in 3D space. That's why I'm just pointing this out as a Cartesian form of the equation of a line. If we think of, we need to get this into y, basically sort of like y equals mx plus b, we can take this Cartesian form, which is good for 3D, not good for 2D space, or that useful. Multiply both sides by u sub 2, and we get, I'm also going to turn this around because that's just an equal sign. We have, with yellow, not white, y minus y sub 1 is equal to u sub 2 over u sub 1 times x minus x sub 1. Let's go ahead and finish getting this into what looks like slope-intercept form, y equals mx plus b. We're going to multiply this through. We have y minus y sub 1 is equal to u sub 2 over u sub 1 times x minus u sub 2 over u sub 1 x sub 1. And now adding that y sub 1 over to the other side, and we have y is equal to u sub 2 over u sub 1 times x. And I'm going to go ahead, because this is going to be a positive term, write it first and have plus y sub 1 minus u sub 2 over u sub 1 x sub 1. Now this cleans up to basically, this is the gradient, this is the slope, the rate of change for a line, u sub 2 over u sub 1, and this whole term here, a couple of terms, y sub 1 plus u sub 2 over u sub 1 times x sub 1, that's the y-intercept of our line. So that's a diagram from the previous page of notes that was over there. And this is basically your Cartesian form of that line in two-dimensional space, and these are the notes that's going to show us on our next example how to move within these three forms when we actually have some numbers to work with. Bam! Example number 1. Given point, or the points, A is 3, 4, and B has the coordinates of 4, 6. Find the vector, parametric, and finally Cartesian equations for line AB. Well, for any new problem, if you are a little bit unsure of how to start the problem, let the formula tell you what you need, right? Let's start with the vector form, because obviously we want to start with the new material, not going back to, like, algebra 1, given 2 points, find the equation of a line. The vector form of an equation is vector r is equal to vector a plus lambda times vector u. To write the vector form of an equation, we need some point on the line written as a position vector. Well, that's simple enough. If a has a coordinate of 3, 4, then vector a, which is a position vector OA, that's going to be the position vector of 3, 4. That vector written in component form as a column vector. Well, now all we need is some lambda, some unknown lambda, some unknown scalar multiple like x and y equals mx plus b, to be applied to the direction vector. Okay. Your direction vector, while it doesn't have to be technically on the line, needs to be created or analyzed or found by using a couple points on the line. So we're going to say that vector u is equal to vector AB, and just simply write the component form of vector AB with the terminal point of B and initial point of A. So we're looking at terminal minus initial, terminal minus initial, and that is going to give us vector u in component form, which is going to be 1, 2, equal to vector r. Well, that's 3 vector 3, 4 plus lambda times vector 1, 2. And that's it. This really isn't much more complicated than just finding the equation of a line in algebra 1. Find a fixed point, only now it doesn't have to be the y-intercept, and find the direction of that vector, or the direction of that line. Now we want to move into parametric form. Well, that's simple enough. Parametric form means all we have to do is remember that vector r is a position vector. That notation is supposed to represent a position vector for any other point that lies along the line. So we'll do this in green. Parametric is going to be some random point, except it's not random. We're going to define where it's at with a lot of other parameters. Some point determined by this initial point with this moving from there with this direction, then setting up, remembering again that lambda is a scalar multiple to both or all of the components, in this case just both components of x and y, we get x is equal to 3 plus lambda 1, 3 plus lambda, and y is equal to 4 plus 2 lambda. Yeah, boom, parametric form. Now, if we want to write this equation in that Cartesian format, we want to basically just eliminate lambda, but we don't want to track that horizontal and vertical movement along the x or y axis in terms of, say, like time. It would have been probably written in your pre-calculus class. We want to eliminate the parameter lambda. So this should sound very familiar to what you learned in pre-calculus. We have x minus 3, unless you're a pre-calculus now. My kids don't have this notation in their pre-calc book. But we have x minus 3 equals lambda, and here we have y minus 4 is equal to 2 lambda. Now dividing both sides by 2, we get y minus 4 over 2 equals lambda. Lambda is the same scalar multiple being applied to each component of that vector, so thus it has to be equal. And so therefore, if x minus 3 is lambda, if y minus 4 over 2 is lambda, well then x minus 3 is equal to y minus 4 over 2. And if we want to continue to move this into, this will look like Cartesian form in three-dimensional, with three-dimensional lines, but it's not very clean. We have a much cleaner format with two-dimensional, of course. We can multiply both sides by 2 and get 2x minus 6 is equal to y minus 4. Adding both sides by 4, and because this is not an inequality, I'm just going to move this around so it's a little bit more comfortable for us to see. Or just, I don't know, I feel like writing it that way. Negative 6 plus 4 is negative 2. So we have our Cartesian format of this line. We have a parametric, a pair of parametric equations, really easy for me to say, for the same line. And now we know how to express the equation of a two-dimensional line in also vector format. Very, very cool. So we're going to take the equation of that line, extend this example slightly, and say, let's find 3 distinct points on the line. Well, remembering that this scalar multiple of lambda is kind of like acting like our x in y equals mx plus b, continue to tie together some of that old knowledge we have with the new stuff, you can plug any value of x you want into the equation of y equals mx plus b and find another corresponding y coordinate. Well, same thing here. We can say, well, let's let lambda equals 0. Well, that's going to be this xy is going to be equal to, I'm not going to do this vector notation for the two distinct points, but some point xy on the line is equal to 3, 4 plus 0 times, because lambda is set to be 0, times 1, 2. And that is going to be simply 3 plus 0 and 4 plus 0 times 2, which is also 0. Our coordinate is going to be just simply 3, 4. And if we let lambda therefore be 1, well, that's going to be 3. Actually, I like it better in parametric form. 3 plus 1 times 1. And y is equal to 4 plus 1 times 2. I'm just taking this in parametric form, x equals 3 plus lambda 1, y equals 4 plus lambda 2, and letting lambda equal 1, and getting this x coordinate is going to be equal to 4. This y coordinate is going to be equal to 4 plus 2, which is 6, and so another coordinate. I just said we needed to come up with 3 distinct points, not specifically for these lambdas, but you can come up with any ones you want, but why not pick the convenient ones? So now, how do you show that 1, 5 does not lie on this particular line? Well, again, maybe we should go ahead and do that. Writing this in parametric form, Since I keep using that, I should have maybe done that in the first place. You just have to take this coordinate of x, plug it into the equation involving x, or you could use the y, of course. Find out what lambda should be for one variable, and then check that answer then with the other components or the other coordinates, parts of that coordinate. I'm thinking of like as we go into three-dimensional space. But we have x is 1. And after subtracting both sides by 3, we have -2 is equal to lambda. Okay, so if -2 is equal to lambda, to, get specifically the x-coordinate of 1, this isn't, lambda's not always equal to -2. It's not a constant. It's just how do you basically move from this point of 3, 4 to this point of 1, 5 with this direction vector. But let's check it. So now we have y is equal to 4. I'm going to use this lambda because it's specific to this point, or this x-coordinate really. I'm checking whether or not the point falls in the line. Okay, well, here's our equation of our line in vector format. Show that this, well, it does not lie on the line, so hopefully we didn't get the same value, but when we plugged x in, we got, for that specific x value of 1, lambda needed to be -2. If that lambda of -2 in our parametric equation where we're looking at y in terms of lambda, if that had come out to be equal to 5, well then that would have shown that 1, 5 was on the line, but we got a value of 0. So really the point 1, 0 is on the line, but 1, 5 is definitely not on that line. Got one more example coming up right now. It's the last example. Example number 3. We're going to write down the vector, parametric, and finally the Cartesian equations for the line going through the point -3, 5 and parallel to vector v. This is just acting as a vector u. It's our direction vector, which is equal to -j. There's a couple little things in this problem to throw us off a bit, but I think we can handle it. We're going to remember that we're going to start with the vector form of an equation. So that's going to be vector r is equal to vector a plus lambda times vector u. Or in this case, because they've defined the direction with the variable v, we're just going to call it vector v. Okay, so you need simply an initial point. Well, that's given to us. That's not too bad. So we're looking at vector r, just filling up the gaps. What is this equation asking for? Give it what it wants. And now we have to talk about this direction vector. Okay, so we don't see it too often, but there's three ways, yes, that's what I was trying to say, to write a vector in component form, right? In two-dimensional space, vector v is equal to a times vector I plus b times vector j, or some other letters that your textbook might be using. Actually, I'm falling back to an old pre-calc book that I use. My current book, and maybe yours is calling this u sub 1 and u sub 2, or in this case, v sub 1 and v sub 2. That can be written in component form as a, b, or v1, v sub 2. v sub 1 and v sub 2, or in as a column vector that I'm using because I'm staying consistent with the book that I'm teaching from for my live class, as a column vector, ab or v sub 1, v sub 2. So when we look at this and see we have just minus vector j, well, that's a movement down one vertical unit vector, because vector I is a unit vector in the horizontal direction or in the direction of the x-axis. Vector j is a unit vector in the direction of the y-axis. And I'm doing this with pause because, of course, the orientation of the x and y-axis is a little bit different for three-dimensional space, which is coming up in the next lesson. But here we have, if it's vector v is just simply minus vector j, then that is basically 0 times vector I minus 1. That's a j. minus 1 times vector j. So we're looking at the vector 0, negative 1. Okay, so that's vector format, and we did that in white. Now in, let's say, orange, we'll find this as a pair of parametric equations. And to do that, we're going to write vector r. Remember that this is a position vectors for any point along the line. Just trying to use that vocabulary that's in your book to get you used to it, and my own kids. And this scalar multiple applies to both the horizontal and vertical component, so we can go across each row and set up a little parametric equation. We have x is equal to negative 3 plus lambda times 0, or just simply x equals negative 3. It's a little bit funny for examples and problems we've been doing so far. Y equals 5 plus negative, or minus, 1 lambda. Okay, and this is our pair of parametric equations. Now, the slightly funny part of this problem is how do we write this in Cartesian form? And this one's going to be a little bit different because, as you saw in the previous example, we eliminated lambda through substitution, and we brought in a relationship relating x and y together. But there's no lambda up here for equation x. So are you going to find that tricky, or are you already thinking of what the answer is? You could look back here. Remember, if you have a directional vector that has no horizontal movement, but only movement down 1, from this point negative 3, 5, the line is simply moving down. It's a vertical line. This has a slope which is undefined. Or remembering that if you have an equation of a vertical line, it's simply x equals that number. So in a Cartesian form, we have x is equal to negative 3. So they can throw in some of these little twists, some of these little special cases. This actually, remembering back in Algebra 1, our vertical and horizontal lines were the simplest equations, at least looking equations, but students, they tend to find them a little bit tricky because they're different. They don't have necessarily a gradient or slope because if, in this particular case, since it's a vertical line, your slope is undefined. When you get that situation where you get to the parametric form and you're like, well, no, wait a minute, I can't eliminate the variable of lambda through substitution because it's not in each of these parametric equations, go back and just look at the geometry that's in your original problem and you should be able to figure it out. I'm Mr. True. Bam! Go do your homework.